Swayam Prabha. Digital India. Educated India.
Welcome back. We will continue our discussion on design of atomizers. We will start by looking at the simplest of all, which is the pressure swirl atomizer, and try to understand a formal design process that we can use to design a simplex atomizer. Now, before we go much further, it is always a good exercise to first have a schematic of what you want your atomizer to look like and the various degrees of freedom that you have available to you at your disposal, say whether it is an orifice size or any other dimensions in there, these are all degrees of freedom that you have available at your disposal, and you have been given a certain set of constraints that you have to meet. So, like for example, you may have a certain supply pressure that is available to you, and you want your atomizer to spray a certain fluid at a certain flow rate. These are all design constraints that you have to obey at the end of your design process. Okay. So, we will start our discussion of design of simplex atomizers. Okay, this is going to closely follow a paper by Chu et al. I will give you the reference, it is AIAA journal volume 42 12 from December 2004. In fact, their process also follows the original work in this field by these two people. This is a classic paper where the first design process for a simplex atomizer was presented. Now, we looked at let us first draw a schematic of this whole of what it is that we are talking about. Okay, we will start by looking at the schematic itself. The atomizer that in question has two parts to it usually. there is a fuel distributor. So, this we will call this part distributor, and this part is often called the orifice plate. So, the simplex atomizer at its heart has two parts to it. Now, the distributor element has a set of tangential slots, and in this case we have shown those to be at some angle beta, and so they are bringing in fluid into this passage here. I will I'll sketch this just to show you. This is all like the passage that is enclosed by the distributor and the orifice plate. I am going to erase this. I just wanted to show you the basic idea of how this works. So, all of the part that I hatched in yellow could be wetted by the liquid that you are trying to spray. So, that is the geometry we are looking at. Now, the distributor element brings in fluid at some angle beta, as well as it having a swirl component. So, if I look at the top view of the distributor plate, essentially it could be a set of slots. Let us say I am showing in this case 2 slots that are coming in at some off axis location R I. The off axis location R I dictates the amount of swirl. Now, I have shown the swirl chamber here to be slightly larger than R I itself. So, the distributor slots are not exactly at the very tangential edge of the swirl chamber, which is sort of more like a practical situation. Now, in this case essentially what we form, because the liquid coming in is at a tangential, has a tangential velocity, you create a swirl in this plane, and that swirl sets up a free vortex inside this region. For a free vortex, we saw that the total angular momentum is conserved, because there is no dissipation, because the flow is irrotational. For a free vortex, the angular momentum is conserved, which I can write as follows. If I want to know what the swirl velocity is at any r location, and if W I is the swirl component of the velocity at the inlet, R I is of course the radius of the slots in the distributor. Now, I could have, like I have shown in this picture, 2 slots, but I could have multiple slots. So, at any r location I have W I. Now, just to clear what W I is, W I would be q times sin beta divided by A P. A P is the total area of all the slots put together. So, for example, in this case, if W is the width and if D is the depth, N times D times W is AP. Okay. Before we go much further, let us write down the list of givens. So, what are all the degrees of freedom that are available to us in the design process and typical constraints. For example, the degrees of freedom available to me are N, D, W, R I, R S, I will add a few more. If this is L S and if this is L O. So, L S is the length of the swirl chamber, L O is the length of the orifice, exit orifice, and of course, R O that I have shown here, which is the radius of the exit orifice. Now, I could also have, let us say, this angle here alpha, the angle of convergence. These are all parameters that are important. Typical constraints that we have to meet are supply pressure is usually specified, flow rate that you want the nozzle to deliver is usually also specified. So, that is Q, we will say that is in meter cube per second, this is in pascals or bar typically. Let us be more engineering rather than SI units, we will say this is specified in bar, this may be specified in liters per hour or liters per second. I have a certain cone angle that I require, say for example, in this schematic it could be that angle there of the liquid sheet exiting the nozzle. And in more recent instances, you may have some sort of an indication of some sort of a requirement coming from drop size. I will use a script D for this. Although we will very quickly see that it is going to only be known after the fact, not really controlled during the design process. Okay, so if I now go back to my free vortex that I have set up by these tangential slots, W times R is W I R I, which is coming from angular momentum conservation. Now, mind you, the moment I say angular momentum conservation, I have already made a couple of simplifying assumptions that we are only dealing with inviscid analysis. Actually, angular momentum conservation alone does not require inviscid this thing, it could be true even in a viscous flow, but we are only going to look at an inviscid analysis, as you will see a little later on. Now, since we made the simplifying assumption of the flow being inviscid, I can now use Bernoulli's equation at any, if delta P is the supply pressure, P is the static pressure at any point in the chamber, U is the axial velocity, W is the swirl velocity. Now, if I go back to the schematic, we talked about this in some detail. One of the main advantages of using a pressure swirl atomizer is the fact that it entrains an air core. So, your orifice size is no longer the determinant as far as the length scale of the liquid coming out of the nozzle. The length scale associated with the liquid can be much smaller than the orifice size itself, and that is one of the advantages of having the pressure swirl like design. Okay. So, let us see what that means here. What that means, what I have shown here in blue is the air core itself. And I am going to call the air core radius as ROA. We will see that it does have a significant bearing to the performance of this nozzle. So, if I have ROA as being the radius of the air core, I can apply the Bernoulli's equation from between the 2 points. If I take a point way upstream here where the pressure is delta P, and if I apply it to a point on the air core here. So, I am applying Bernoulli's equation between this point way upstream of the atomizer where the fluid kinetic energy is very small and all of the, and basically U and W are 0, and to a point just on the liquid, in the liquid, but on the air core periphery. So, if I apply Bernoulli's equation between these 2 points, what do I get? I find that delta P is equal to half rho U 0 A squared plus half rho W O A squared, where U 0 A is the axial velocity at the air core and W 0 A is the swirl velocity at the air core. I think at this point it is good to take a small detour down the lane of undergraduate fluid mechanics again. Remember, Bernoulli's equation is only applicable on a streamline. Now, if I take a streamline coming to this air core all the way extended into the tank. So, if I can draw a streamline going from this point here all the way into the tank, which is at some high elevated pressure delta P, we are applying this Bernoulli's equation on that streamline. I can also apply it from that same tank to another point, let us say here or here, does not matter, but if all the streamlines are originating from the same tank, I can apply this Bernoulli's equation between any point inside this swirl chamber and the tank, okay, which also means since the tank is at a constant supply pressure delta P, it also means I can essentially apply Bernoulli's equation between any 2 points inside the swirl chamber even if they are not on the same streamline, because I can apply Bernoulli's equation on 2 points on a given streamline, and if all the streamlines are originating from the same stagnation pressure delta P, I can essentially apply Bernoulli's equation even across 2 streamlines at 2 different points, because they are all amounting to the same stagnation pressure. We will take advantage of this later on. So, now back to, so we have our delta P, which is half rho u 0 a squared plus half rho w 0 a squared. Now, what is u 0 a? That is the axial velocity in this region. And w 0 a happens to be the swirl velocity. So, we will write some simplifying expressions for that. U 0 a would then have to be q divided by a 0 minus a 0 a. Okay, a 0 a is the area of cross section of the air core. A 0 is of course pi r 0 squared. W 0 a I can get from our angular momentum conservation as that q r I over A p is the linear velocity or speed of the liquid coming in. So, let us make some notes here. This velocity vector has a magnitude of q over A p, and the component that is in this plane here is q A p sin beta, and that times r I is the angular momentum essentially, times rho of course, but we are going to instead of writing rho V r, we are just going to write V r because rho is constant everywhere. Okay, so, I can now substitute these two equations into the Bernoulli's equation at the air core. What do I have? Delta P would then become half rho Now, we define a discharge coefficient just like we would define, let us say, for flow in a pipe or flow past a flow through an exit orifice or sorts. We were actually introduced to this earlier on. We used the terminology flow number, and we showed how that flow number is going to be dependent on some system of units that you have. We are now going to define figure out a way by which we can make it relatively unit independent. Okay. So, I can now define a discharge coefficient as follows. Q by A naught is the, so A naught is like the total cross sectional area available for the flow. So, we are defining this discharge coefficient as though we have no swirl, it is just flow through an orifice. When I substitute Q from this expression into the equation for delta P, after some just a couple of simplifying steps, we find this. I have introduced a couple of new terms, new symbols here. Let me go ahead define them. X is A0 A divided by A0, which is like the fraction of the cross sectional area that is occupied by the air core. X is physically the fraction of the cross sectional area that is occupied by the air core. K1 is this dimensionless group AP over pi R0 RS. Okay, you can clearly see K1 is dimensionless, so is X. So, I now have an equation relating CD to X and I also have K1. Now, K1 is what I am after, K1 is something I need to get a value for before I can design. CD is something that I may actually know apart from A0. So, if I assume an A0, if you look at this expression here one more time, if I know A0, I know CD because Q and delta P are given to me in the form of constraints. I have a supply pressure and I have a flow rate I need to deliver. So, for a given A0 I can find a CD. So, if I have a CD, I still have only one expression down here coming from our Bernoulli's equation, which relates K1 and X. X is still something we have no handle over, that is determined by the fluid mechanics inside the atomizer. Okay. Apart from of course Ri over Rs and sin beta, these are all also design variables, degrees of freedoms that are available to us, and we have only one expression. So, herein comes a simple principle that is often invoked to fix the value of X. Okay, this is called the principle of maximum